Here we have a beam section only, so meaning that you will not need to do moment diagram. Okay, so we have this beam section is subjected to M, that is 7.5 Gibbs feet. Okay, so in the beginning, this M just equals 7.5 Gibbs feet, but normally we use what? We use pounds inch. Okay, how to convert it? It will be 7.5 times 12,000. Okay, it will just convert it into pound inch. But what is the sign of this bending moment? Okay, look at the directions of the bending moment M. Okay, if you add this bending moment, then this section will be deforming in this way. Right, so on the top, it will be positive in tension. At the bottom, it will be in compression, negative. Right, so this is a negative bending moment. Right, so strictly speaking, it should have a negative sign. But again, we will not carry this negative signs when we calculate the stresses. Right, so it doesn't matter. So we have this section and this bending moment, and find the magnitude of bending stress at a point 3.32 inch above the centroid. Right, so we have two steps. The step B will be the final question, and step A will be just the intermediate step. Okay, so in step A, we will calculate the distance of the centroid from bottom. That is, calculate the y bar, and the moment of inertia is calculate the I and the controlling section modulus. Okay, so we will just do exercise to use these two equations and two tables to find out y bar and I in the beginning. Okay, so in step A, we're calculating y bar. Right, our y bar just equals sum AI yi over sum of AI. Right. So in this example, we can just simply cut it into three sub areas. Here we get area 1, area 2, area 3. Right, the local centroid had been assumed here. We have assumed this global centroid here. And we are calculating this y bar. Right. So here we have the local centroid. Here is your y1, and local centroid of area 2 is here. This is your y2. Here, this is your y3. Right. So in the first table, the key is to find the correct yi, the y values. Right. So here, our first table, you have area 1, area 2, area 3. Right. The A1 would be what, 10 times 2. Right. 10 times 2, that will be 20. And A2 will be 2 inch here times 8. Right, just 8 times 2, that is 16. A3 will be 6 times 2, 12. Okay. And the y values, the y1 will be 2 over 2, right? The half of the thickness of area 1, that will be 1. Right, the y2, that will be the thickness of area 1, 2, plus half of the thickness of sub area 2, 8 over 2. Right, so we get 6. And y3 will be the thickness of area 1, that is 2, plus the thickness of area 2, This is 8, then plus half of the thickness of area 3. This is 1. Okay, we got 11. Then we can calculate AI, YI. So here we get 20, here we get 96, and the bottom just 12 times 11, 132. Okay, then we can sum here, you will get 48. And here you will have 248. Okay, so the Y bar here equals 248 over 48, get 5.17 inch. Okay, in the second step, of step A, so we're calculating the I, that the equation is the sum of ICI plus AI DI square. Right, again, we just use this table. Have area 1, area 2, area 3. Right, so here you have AI to be 20, 16, 12. And the DI equals what? YI minus Y bar. Absolute values. Right, so the first one, D1, will be 1 minus 5.17 absolute value. That would be 4.17. And the D2 would be 6. Right, 6 minus 5.17. That would be 0.83. And the D3 will be 11 minus 5.17, that is 5.83. And the ICI will be what is a BH cube over 12. Right, for the first one, the sub area 1, that will be 10 times 2 cube over 12. 6.7. And for the second one, that will be 2 times 10 times 8 cube over 12. 85.3. Right, for the third one, that will be 6 2 cube over 12. Get 4. Okay, then based on these values, the I can be calculated as 12 times 4.17 square plus 6.7 plus 16 times 0.83 cube square plus 85.3 plus 12 times 5.83 square plus 4. Okay, the result here would be 862.7 inch to the fourth. Then we're also requested to calculate the section modulus. Okay, the section modulus as we defined, it is the S top equals I over C top, and the S bottom will be I over C bottom. Right. The I has been calculated. Right, it's 862.7 over C top. Right, C top. This is critical. So what is C top? C top is just the overall thickness, that is 2 plus 8 plus 2, that is 12, minus y bar, right? Minus y bar, that is 5.17. Okay, this will be 126.3 inch cube. And here will be 862.7 over, and here the bottom will be, what will be this 5.17. Okay, since this is just the distance from the bottom, y bar is the distance of the centroid to the bottom. Okay, so here this C bottom is just directly 5.17. Okay, so here is 166.9. So you can see that in this example, because this shape is a composite section, it's not symmetric. Okay, so our C top and C bottom will be different, will be not the same. Okay, then we're done with question A. Then let's look at part B. Then we're calculating the bending stress at K. Okay, bending stress at K is just the M times YK over the I, over I. M, as we mentioned in the beginning, that is 7.5 times 12,000 times YK. The YK is 3.32, right, over 862.7. Okay, this would be 346 psi. Tension or compression. Okay, as we analyzed, this will be above, this K is above the centroid, right? On top of it, it will be in compression. Bottom or below the neutral axis, it will be in compression, and on top of it or above the neutral axis, it will be in tension. So this will be positive. Okay, so what is the maximum tensile and maximum compressive bending stress? Again, this according to this analysis, the maximum tensile stress will be here on top, right? Maximum compressive stress will be here on the bottom. Okay, so the maximum bending stress, tensile bending stress, that will be on top, right? So this can be calculated from M over S top will be 7.5 times 12,000 over S top, that is there, that's 126.6, 126.3. So this would be 712 psi. And the maximum compressive stress, it will be on the bottom, it will be M over S bottom. The same bending moment over 166.9. Okay, this will be 539 psi. And here will be tension, will be compression.